So continuing in our titration calculations, let's look at what happens after the equivalence point. So now we've added 30 milliliters of sodium hydroxide. The equivalence point was at 25. Normally with the indicator titration, we don't go past, or not intentionally. But here we're measuring the pH or calculating it, and so we're interested in what happens afterwards. So here we're going past the equivalence point. So we've neutralized all of the weak acid. We've converted that into conjugate base. But the contribution from the conjugate base is not important anymore because we have this strong base that's added, and that completely overwhelms any contribution by the conjugate base. So here we have before addition, after addition. So we've used up all of the acid, converted that to the conjugate base, and we have the hydroxide here. This may look significant, but this is weak, and so it's not going to come back very much. And so all we have to do is find the pH based on this amount. So it's not quite that simple. So I'm just really not liking this whole moles business. So this is 0.50 millimoles. Okay, 1, 2, 3. So 0.5 millimoles of sodium hydroxide. And to find the molarity of sodium hydroxide, we need the total volume of solution. So the volume of the solution is going to be the original 25 milliliters plus what we've added of the sodium hydroxide. So I think that's 55. So to calculate the molarity of the hydroxide ion, we can take the 0.50 millimoles and divide by the 55 milliliters, and we get moles per liter. 0.009. And then it goes 0909. It's one of those kind of fun repeating numbers. And the unit is molarity or moles per liter because the millis cancel out. So we have hydroxide ion concentration. We can calculate the pOH. We know that the pH is going to be 14 minus the pOH. The pOH is 2.04. So the pH is 11.96. And it looks like that's correct based on what the graph is. Any questions? These different parts of the titration curve are different situations in terms of acids and bases. And I guess there's some memorization that could occur here. But the way I approach it is I just try to think about, okay, well, what's happening? Here's this acid and this base, what's going to happen? And you can assume that whatever hydroxide is added reacts completely with your acid, and because that's going to be mostly true. And then you figure out what these concentrations are. Then you take into account any weak acid, weak base behavior of reconverting to the other thing. If we continue on, 35, 40, 50 milliliters, it's the same idea. For all of these, our amount of extra, nope, that's not true. Let's just look at this real quick. Let's look at the 50 milliliters. So 50 milliliters of 0.1 molar sodium hydroxide is going to give us, what, 5 millimoles of hydroxide. Originally we had 2.5 millimoles of acid, right? 25 milliliters times 0.1. .5 millimoles of the acid. Just stop me if I screw it up. So hydroxide plus acid making water that we don't care about, and A minus. So before the addition, I had 2.5 millimoles of the acid, and the addition is adding 5 millimoles of hydroxide, and so after the addition, I'm going to use up all of my acid. I'm going to have 2.5 millimoles of that left, and I'm going to have 2.5 millimoles of the conjugate base over here. Is everybody following on that? So I'm completely reacting my strong base with my acid, and then that's going to tell me what I've got left here. Because I've got so much of this strong base here, the hydroxide, I don't have to consider what this is going to do. I could, but it's not going to be significant. So I just need the 2.5 millimoles of sodium hydroxide. So 2.5 millimoles hydroxide ion. Oops, I'm going to combine those. And my total volume is now 75 milliliters. So 2.5 divided by 75, another fun repeating number. That's the hydroxide ion concentration. So we can calculate the pOH. Ooh, that's fun. I better show you the whole thing there because you're not going to believe me. Let's calculate the pOH. Oh, I see what I did there. Anyway. Sorry, I got a minus sign in the wrong place. The pOH is 1.48. And so the pH is going to be 12.52. Any questions? This is a great summary slide, summary illustration. So here we have our pH curve. Initial pH, we just consider it's a weak acid. In this range here, before the equivalence point, it's a buffer. You can use Henderson-Hasselbalch unless you want to be very precise. At the equivalence point, you're looking at a solution basically of the conjugate base. And then after the equivalence point, you've got excess hydroxide. So each of those parts of the graph uses a slightly different approach to the calculation. Any questions? So here's a question for you. Now this is chapter 17, so it's not on the exam on Thursday. But do you think I might ask you to do calculations from different parts of that curve on the exam? Yeah, probably. Here's an example. A 40 milliliter sample of 0.1 molar nitrous acid is titrated with 0.2 molar KOH. Calculate the pH at the equivalence point. So at the equivalence point, the moles of acid are equal to the moles of base. So we can figure out, and we need to figure out, what volume of potassium hydroxide has been added, because we need to be able to calculate the concentration of hydrogen ions. So we can approach this like a regular titration. Here we've got, I'll just write the equation real quick. It's a monoprotic acid. We're going to talk about polyprotic in just a minute. So I've got 40 milliliters of nitrous acid, and the concentration is 0.100 moles per liter, and I have 0.2 molar KOH. So I'm just going to use stoichiometry. So 40 milliliters of the acid, and I'm going to use the molarity of the acid, millimoles, HNO2 per milliliter, so those guys cancel. And then 1 millimole of KOH per 1 millimole of HNO2. And then I've got 0.200 millimoles of KOH per milliliter. So 20. I've added 20 milliliters of KOH at the equivalence point. So I've got hydroxide that I've added to my acid, and that's reacting to form nitrite ion and water. Before the addition, I had 4 millimoles of the acid. 40 milliliters times 0.1 moles per liter gives me 4 millimoles. So I've got 4 millimoles of acid and none of anything else. The addition, I'm adding 20 milliliters of 0.2 molar, and that at equivalence point had better be the same number of millimoles as the acid, right? Because that's the point of the equivalence point. So afterwards, I've got none of this and none of that, and 4.00 millimoles of the NO2 minus. Any questions about that? At the equivalence point, what I'm going to do is I'm going to take this number of moles, find its concentration. What I have is a weak base situation, right? So the molarity there of the NO2 minus is going to be the 4 millimoles divided by the total volume. I've added 20 milliliters of KOH to 40 milliliters, so the total volume is 60. So I've got 0.0666. Are you okay with that? I'm going to erase this because I need some space. So we're going to look at this as a weak base, because it is. And we're going to make an ice table. So my initial concentration of nitrite ion is 0.0667. And that doesn't matter. This is 0, this is approximately 0. The change is that this is going to go down by x, and each of these is going to go up by x. So we end up with 0.0667 minus x, x, and x. So now I've got a Kb situation, right? Because this is acting as a base. So Kb is equal to HNO2 times H3O plus divided by NO2 minus. So I've got these terms I can plug in. So I'm going to end up with x times x, or x squared in the numerator. And in the denominator, I'm going to get 0.0667 or so minus x. But I need a number here. Right? So I'm looking up in the table from the textbook the pKa for nitrous acid, HNO2, is 4.6 times 10 to the minus 4. Ka 4.6 times 10 to the minus 4. What I need up here, though, is Kb. Ka times Kb is 10 to the minus 14. So Kb equals 1.0 times 10 to the minus 14 divided by Ka. I'm getting 2.17 times 10 to the minus 11. Okay. Now, we can definitely plug this into our solver. Would x is small work for this, do you think? Yeah, it should. This is really a small equilibrium constant. So this is not going to go towards making hydronium ion very much. And so this x relative to the 0.06 is most likely going to be small. So x is small means that we don't have to consider this one. And unlike some of the earlier ice tables and equations, taking that out does make this a simple calculation. I think it is faster than using the solver. So I've got my Kb. I'm going to multiply by the denominator there, 0.00667. And then I need to take the square root of that. And I find that x is 1.20. Man, I forgot. 6 times 10 to the minus 6. And then we always need to ask ourselves, what does X represent? Because sometimes it's the thing we're looking for and sometimes not. Yeah, here, X represents the hydronium ion concentration, which is what we need to calculate the pH. So this equals hydronium ion concentration. And I'm sorry, this slide's just a mess, but it's nothing compared to your worksheets. Oh my goodness. So the pH will be the negative base 10 log of that number, 5.92. Okay, that's not right because the pH is supposed to be above 7. So then here I got all my work right out here, so it took me a minute, but I got help from the peanut gallery. I wrote this expression wrong. Here I've got a weak base reacting with water, making an acid and hydronium. No. There's the mistake right there. That's OH minus. So this is the hydroxide ion concentration. This is the POH. And so pH is 14 minus that. 8.08, that sounds a lot better. I screw up too. Yeah.
How do you determine to use KB instead of KA?
How do I determine, why did I use KB instead of KA? How did I know to do that? Well, I made a bunch of this, right? I'm totally reacting all of my acids, so all I've got is a conjugate base. So I'm going to look at the conjugate base and what is it going to do? It's going to act like a base and it's going to make some hydroxide. So this is the exact reverse of the acid equation where we have HNO2 ionizing to form H+, right? So we can't use Ka here, we have to use the reverse of it, essentially. And that's a common mistake, is that, you forget to do that. And you can look, maybe you could find it online, but you're not going to be able to find it in your textbook. What's the Kb for NO2 minus? It's not there in the list of bases. Because if you need that, it's coming from the acid, and so you calculate it from the acid. It's a good question. So some of you, as I'm grading your worksheets and things, are really good at showing your work, and some of you not so much. And when you get the correct answer, it probably doesn't matter too much how much of your work you showed. But I think it's just really a great mental exercise to be able to write it out. Even if it gets kind of messy, and I'm limited to the one screen here, so I kind of went around and up and down and all over the place. But it's all there. And then when I came up with this answer that didn't make sense, I could go back and look and check things. And especially on an exam, that's a really good thing to be able to do. Instead of solving the problem all over again, to be able to just go back and check your work. Because there's any number of places I could have made a mistake. Any of these calculations, I could have punched a number in wrong. So if I didn't find this as a mistake, I could go and check all the math. Make sure I copied the number, because you write this down from over here, you could lose a 0, you can gain a 0, all kinds of weird things can happen. So show your work. Any other questions about this problem? You can also titrate weak bases with strong acids, and the calculations are very similar, they're just sort of reversed. So it'll start at a high pH and go to a low pH. The buffer region is going to be up here. The half equivalence point, the pH should equal the pK. Oh, now there's a good question. I don't know the answer to that one. Does pH equal the pKb or the pKa? I suspect it's the pKb. At the equivalence point, a calculation very similar to what we just did, where you react all of the base and then you look at the conjugate acid. So I think I just figured out the answer to my own confusion here. When calculating pH in the buffer region, you use pKa for the conjugate acid because you're calculating pH. If you wanted pOH, you would calculate using pKb. We don't do these very often, but related but strangely different. Polyprotic acid. So here is sulfurous acid being titrated with sodium hydroxide. If conditions are right, you can actually see both equivalence points. So here's the first proton being titrated, and here's the second one. The second equivalence point will be exactly the same volume, the same number of moles of base needed as for the first equivalence point, because you are reacting the same number of hydrogen ions. For this acid, the first Ka is 1.6 times 10 to the minus 2. The second one is 6.4 times 10 to the 8th. Those are significantly different from each other, and so you will be able to see two equivalence points. Some polyprotic acids, their multiple Kas are closer together, and so if you do a curve like this, they're going to kind of mush together, and you're not really going to see distinct equivalence points. Any questions? Indicators. Now this might be interesting to you because for your experiment, you need to pick an indicator that might be appropriate for your weak acid. So we can use a pH meter or we can use an indicator. The indicator is going to change color and signal our endpoint. And the endpoint is where the color change happens. The equivalence point is where you have equivalent amounts of acid and base. If you've got the correct indicator, those will happen at the same place. If you have the wrong indicator, you're going to be off. So here we have phenolphthalein, and we're titrating, just guessing from this equivalence pH, is this a weak acid or a strong acid? The pH at the equivalence point looks like about 8.6 or 8.7. That's a weak acid. If it was a strong acid, the pH at equivalence would be 7. So when it's acidic, the solution is colorless, and as we get to the end point, the color just begins to change, and so that's where we know to stop. If we continue, then the rest of the indicator will change color, and you'll get a more intense color. So you've used indicators. Have you ever wondered, what the heck are these things? They are weak acids. Weak organic acids. This is the structure of phenolphthalein, which is one that we use a lot. And you can see why we just call it phenolphthalein instead of its formula or drawing its structure. It's kind of complicated, right? So when this interacts with an acid, we've got some changes that occur, right? And that's, you know, when you take OChem and you'll learn about all of that. I'm sorry, when we add hydroxide, this happens. When we add acid, it goes back to this. So we've got these changes that occur. That causes the color of the compound to change. And it's a very intense color, so we only need a tiny amount of the indicator. If we needed a lot, it wouldn't be useful, because then we'd also be titrating the phenolphthalein. It would be affecting the pH, but there's so little of it that it doesn't matter. Here we see at different pHs what the color of the solution is. So pH 2, 4, 5, 7, those are all acidic and neutral. And around 9, we're in the middle of it changing color. And then up here at 10, it's fully changed. So pH 9, where that changes, that's good for a weak acid, right? Because the equivalence point for a weak acid is going to be up around 8.5, 9, somewhere. This is not going to be the best indicator for titrating a strong acid, because a strong acid will reach its equivalence point at 7, pH 7, and the phenolphthalein isn't going to change. So you'll go past the equivalence point every time. Indicators are going to change within a range of 2 pH units that are centered at the pKa. So here's a different indicator. It's called methyl red. It goes from a purple color to a yellow color, and this pH 5 is, I believe that's going to be where the pKa for that is, because that's the middle of the color change here. So you can calculate this, the pH equal to the pKa, that's going to give you the intermediate color, pH equal to the pKa of the indicator plus 1, that's going to give you the conjugate base form of the indicator, and pKa minus 1 will give you the acid form. So here is a very colorful table showing different colors for the different indicators. These are not the only ones, but these are the common ones. And you can see they give quite a range of pHs. So here's our friend phenolphthalein down here. And on this graph, we see that phenolphthalein is going to begin changing around 9. So that's about where its pKa is. And so this is going to be useful for acids with a pKa of 9. So you can choose an appropriate indicator for your unknown acid based on your calculated Ka value. And there could be more than one correct answer. Any questions? Yeah. That's a good question. Which pKa for your unknown acid? Hopefully many of them will agree quite well with each other. For that midpoint one, if your graph method and your calculation method disagree, I'd go with the calculation method, especially if it agrees with your other ones. They should match up. There's only one Ka for your acid. Yeah. So they should be the same or close, because it's not perfect. No, there's only one Ka. You can calculate it from different regions, different information that you have. The one that's most likely to conflict is that graphical one where you look at the pH at the midpoint and you say, oh, that's the pKa. It might be, but for some it's not.